Okay, so hello everybody. My name is Milan Dojcinovski. I'm from the DBpedia core team based in Leipzig, Germany. And I would like to welcome everyone to the DBpedia Knowledge Graph tutorial. Let me share my screen with the slides. Okay, great. I think you can see my screen. Can someone confirm this?
Yes, we can.
Okay, perfect. So, yeah, as I said, welcome everyone to the DBpedia Knowledge Graph tutorial. This tutorial is exclusively developed and shaped for newcomers, for people that have very little knowledge about DBpedia and would like to learn more about the DBpedia Knowledge Graph and the community behind it and the project itself. So together with me are here my colleagues, Jan Forberg and Johannes Frey, that will present interesting stuff around DBpedia and interesting and relevant technologies. This tutorial was supported also by our colleagues Julia and Sebastian. So yeah, as I mentioned, we are part of the DBpedia core team. We work on the core technology behind DBpedia. Each of us has a dedicated task within the team and with some particular expertise, and we will present our expertise and knowledge that we have about DBpedia. So the tutorial, as I said, it's dedicated for newcomers and exclusively it is shaped to get people familiar with the DBpedia Knowledge Graph. What does it mean? It means it includes the extraction process, how the knowledge graph is being extracted, how the release process works, and how the data that is being published is organized into knowledge graph partitions, which is also very important so that you can pick individual pieces of information that you find relevant for your use case. The tutorial is also focused on the technology. So there are things such as the DBpedia Databus platform, which is the core middleware, I would say, where the data is being published and announced for consumers. And then we have the other parties on the DBpedia services such as DBpedia Spotlight, Lookup, and the Sparkle endpoints that we offer to the end users. So in this tutorial, you will also learn about how to replicate the DBpedia infrastructure, and also the last part of the tutorial is on an imaginary use case on the topic of semantic indexing and search using the DBpedia technology stack. So in this use case, you will learn and maybe we will motivate as well that you think about how you can use and what you can do with DBpedia. This use case is about indexing text documents with DBpedia technology and then executing semantic queries on top of this with help of DBpedia Knowledge Graph. So more about this later in the second half of the tutorial, and this will be presented by my colleague Jan. Yeah, so the whole tutorial is organized into 4 chapters. The first is to introduce the DBpedia Knowledge Graph in the nutshell. So it's very general information about DBpedia, how it's organized and how technical it works. The second part is more practical. There I will present some interesting queries so that you get the feeling about what you can do with DBpedia, what data is behind DBpedia, and what interesting information you can derive by querying DBpedia. The third chapter of the tutorial is dedicated to the local infrastructure. So you will learn about how to deploy and use DBpedia on the local host. Then we will see how we are with time, but the idea is to have a short break with some Q&A session. And then is the fourth chapter, which is exclusively on the use case about semantic indexing, search, and search using the DBpedia tag. So that's basically the agenda of the tutorial. And if you have any question, please write down your questions in the chat. After each chapter session, we will look at the chat and check if there are any questions, and we will try to answer your questions. If there is no time enough to answer your questions, please drop your questions afterwards by sending us an email, or you can join our DBpedia Slack channel, and we will be happy to answer your questions there. Third option is to put the questions on the DBpedia forum. These relevant links I will provide later in the tutorial. Of course, you're muted for a better call hygiene, and if you want to follow the slides during the tutorial presentation, you can do this by visiting the link and getting access to the slides. So if you type down tinyurl.com/cdv21 DBpedia, you will get an access to the slides. So they are publicly available, and you can already follow them online. Yeah, so let's start from the beginning. So let's start with the question about what is DBpedia and how it all started, because this is very important so that you get a good understanding about the motivations at the beginning and how over time the DBpedia developed as a community project. So it all started in 2007, when several people, enthusiasts, had the idea about what about if we have the information that is in Wikipedia in a structured format, so that we could query Wikipedia as a database, same way as we query using SQL regular databases. So that was the initial idea back in 2007, where DBpedia was established as a crowdsourced community effort with the goal to extract structured information from Wikipedia and make this information available on the web for free for everyone to access and use this information. This initial idea and mission of DBpedia is still valid, still holds true. However, over the years, the focus of DBpedia slightly extended. So the current mission of DBpedia is to provide a global and unified access to knowledge graphs. Some of you might be familiar with the Linked Open Data Cloud, which is an initiative about publishing data according to the linked data principles, which includes also the linking aspect. So over the years, many datasets, over 100,000 datasets have been published following the linked data principles, and these datasets, in order to support the fourth principle of the linked data paradigm, which is the linking, they started establishing links with DBpedia. So over the time, the link set has grown significantly, and by having these links, you can provide a global and unified access to other knowledge graphs. So not that just you can exploit the knowledge that is behind DBpedia, but you can get an access also to third-party knowledge graphs, which are also publicly available as part of the Linked Open Data Cloud. So the DBpedia has moved to so-called global DBpedia, which is just data beyond Wikipedia, which includes three things. The first are the links to other knowledge graphs, but also links to authoritative sources. Then we have the second component, which is the platform, which you can use to integrate data with other data. Here comes into play the database platform. And the third component is the aspect of fair linked data. Probably most of you are familiar or have heard about FAIR principles: findable, accessible, interoperable data. And DBpedia supports and applies also these principles on the topic or on the in the context of linked data. So these are basically the three, let's say, extensions or new focuses of DBpedia, which are the links to the authoritative sources, the platform for matchmaking data so that you integrate data with other data sources, and the fair linked data aspects. This is a very nice figure which illustrates the history of DBpedia. It all started in 2007, where the framework, the tool has been initiated and first versions developed and the first extractions has happened. So the knowledge from Wikipedia has been extracted and exposed into a SPARQL endpoint and published as linked data. Next, we see in 2009 a lot of research around linking. So people start to link data and most of these links are links pointing to DBpedia. So it's very important that DBpedia has been deployed at that time. In 2011, big players such as IBM, Yahoo, BBC, Siemens, Unicode, they started using DBpedia as a use case. So IBM has used in the IBM Watson Jeopardy challenge, where for the first time machine won the challenge. Yahoo has been also using DBpedia, BBC, including links, Siemens, Unicode for abbreviations and language codes has been using DBpedia Knowledge Graph. So we see already in 2011 some adoption by the industry. Between 2012 and 2016, there has been a significant effort on expanding DBpedia from English only to other languages. So it has been internationalized and currently it covers over 130 plus languages. In 2014, there was a need to have a proper coordination of the DBpedia efforts. Many people have been contributing to DBpedia, but there has been no central coordination entity. And for these purposes was established the DBpedia Association, which is based in Leipzig. Then we have also other standardization efforts, such as the Shapes Constraint Language, Shackle, which probably some of you know and you are using this. So this is a W3C standard recommendation, which has been developed actually by people from the DBpedia core team. So this standard was actually validated and developed and inspired by some of the challenges that we had within DBpedia. And currently in 2021 we have over 22 billion of facts. DBpedia is between the most connected data sets in the linked open data cloud, and we are still progressing further and improving in this direction. It's very important to understand how DBpedia is organized. So there are around 20 DBpedia chapters. These chapters are around different languages, data about regions. So there are regional chapters for cities or individual countries. One of those chapters was developing the Dutch National Knowledge Graph, which is a very interesting use case. Then we have the domain chapters, chapters exclusively dedicated for different domains such as law, medicine, media, science, and these chapters they host and maintain a localized DBpedia version. We have also over 30 plus DBpedia members, about 40% coming from the industry and some of them 40% non-profit organizations, but there are also about 20% of tiny and self-employed members. Yeah, so in overall, we have the DBpedia Association in the middle, which coordinates all the effort. Around the association, there are DBpedia chapters around different languages or domains or regions. Then we have DBpedia members, which vary from companies, non-profit organizations, startups, and self-employed and tiny entities. And as a team, we offer these different professional services that you can get from us. So very briefly, about the DBpedia members. We have around 30 plus members from different industries, from different domains. You can see their logos here. Maybe some of you are also present on this call. So we are happy that we have support basically from all these different members which recognize DBpedia as an important technology. Okay, so let's go to something more technical, and let's look at the overarching DBpedia KG release process. The whole DBpedia KG release process is organized into 4 phases. It starts by definition of mappings and ontology editing. This is when we define the mappings from templates in Wikipedia to the DBpedia ontology. The second step is the actual extraction. So the DBpedia information extraction framework is executed on a regular basis. So every month we run the extraction and we extract knowledge from every Wikipedia language. Follows the parsing and validation because we want to have high quality data. Then we have the 4th step, which is the release of the data artifacts that are generated on the database platform. And then follows the ID management and fusion, which is basically a step which combines all the data from different language editions and sync them together, fuse them together. And the very last step is the deployment of the resulting KG, publishing this as link data and on the Sparkle endpoint. This is just an illustration about the infrastructure. We have in the middleware, which is the database platform, where all the artifacts are being published so that you can reference, search, and consume them automatically. The DBpedia extraction framework is a tool dedicated for the extraction process. Then we have DBpedia Live, which is a live version of the tool, live variant of the tool, which in real time extracts knowledge from Wikipedia as soon as some edit is introduced in a particular article, and then this is also reflected into the DBpedia Knowledge Graph. And down below you can see some services such as the DBpedia Spotlight, DBpedia Lookup, DBpedia Archival, which are services that are consuming the knowledge graph and working with the database platform. Let me check how are we with the time. Okay, good. Here's an example about how DBpedia actually these mappings work. So we have on the left side an info box, which is basically a template that you can find on every page Wikipedia article, and on the right side there is this info box. The information within each Wikipedia article is written in a so-called wiki syntax, and in the top you can find these info box templates. Here is the info box type of settlement, and there are these properties that you see actually in the Wikipedia article. So there is the name, official name, native name, language, etc. And what DBpedia does is mapping this information to the DBpedia ontology. These mappings are maintained on the mapping server. So there is a dedicated mapping server where these mappings are defined, curated, updated. And here is an example about this. So these are the mappings for the infobox template settlement. Okay, what is important to understand about the extraction process, that there are 4 main extractions. The first is the mappings-based extraction, a rule-based extraction, which is basically the one that I just show you here. Based on the information and the templates and some mappings, the information is mapped to the DBpedia ontology. Then we have the generic extraction. That is an extraction which is generic, as the name says. What does it mean? It means that it does not use any rules or mappings, but on the fly, the information is mapped to the DBpedia namespace. So then there is no ontology behind it, but this assures that we have a high coverage of the information. Then we have the text extraction. The text extraction extracts not just the information from the info boxes, but also the information from the article's content. So the text with its structure, sentences, paragraphs, sections, subsections, and links are extracted and provided to the users in a structured form. And the last four major extraction is the Wikidata extraction. So this is extraction which maps the information from Wikidata to the DBpedia ontology. And by doing this, you have a unified view over the information in DBpedia and Wikidata. In addition to this, we have the fusion process and the global ID process. The fusion basically provides a unified view over the information from different languages, and the global IDs provides a unified identifier system. So all these different identifiers for entities in different Wikipedia languages, they get a single identifier within the global ID namespace. And this is everything. These are the 4+2 core extraction processes. Here's an illustration just for the mappings-based extraction. That is the server. There are mappings for over 40 languages, and this process generates 6 data sets. And you can see here basically on the left side the syntax, the XML dump from Wikipedia, and on the right side the mappings as they are defined. I can also show an example of the mappings. So if I go here, edit, and here is an example about a particular mapping. So basically this is these are a list of conditions. So this is a mapping for the property settlement type, and if the value says metropolis, then this information will be mapped or will be considered as a city. If the settlement type is municipality, then this will be considered as a town. Then we have this is basically the same, which illustrates the mapping. So if there are properties such as area total and area urban kilometer square, then these properties are mapped to there are mappings which map this information to the DBpedia ontology. So from the mappings in the mapping server, then we get these triples here, which is basically a triple saying that the total area of Prague is 496 square kilometers, and the urban area is 298 square kilometers. Then we have the generic extraction, which maps the information based on no mappings at all. So the idea is to have a larger coverage here, and this information is mapped to the dbpedia.org property namespace. So if you just look to, let's say, the page about Prague, with all the triples listed here, you can see these properties, and if you see the prefix DBO, this means that this relates with high probability to the mappings-based extraction, and these properties are defined within the DBpedia ontology. And if you see the prefix or the namespace DBP, let me find one, DBP. Okay, here is something. So DBP area, DBP humidity here, and these properties are from the generic extraction. So on the fly, these properties are defined and triples are being generated. Yeah, generic extraction is about mapping these properties from the info boxes that are not mapped, or but also they are extractors for extraction of other interesting information from Wikipedia, which are the categories, interlanguage links, labels, and a few others. Yeah, this is just an illustration of the generic extraction, how it works. The properties are in real time mapped to the DBpedia property namespace. Then we have the text extraction, which, as I said, extracts the information from the article content. So sections, subsections, sub-subsections, paragraphs, links, all this information is extracted, modeled, and published. So then you can query basically this information using Sparkle. So all the data is published in RDF. Very, very interesting data set. I suggest you have a look at this. Then we have the Wikidata extraction, which is extraction and mapping the information from Wikidata to DBpedia. It's very similar approach to what we have seen as with the mapping-based extraction. So basically the idea is to map each property to from Wikidata to DBpedia. Here is an example of the P625. Those familiar with Wikidata know about this system of identifying properties and type of information in Wikidata, and this is basically a geolocation. And this is mapping here how this information is mapped to DBpedia namespace. So if there is something such as P625 in Wikidata, this is mapped to DBpedia and considered as a spatial thing. And then we have the latitude, the longitude, and the geo-RSS point also provided. So this is just one mapping for the spatial things in Wikidata. The DBpedia ontology, that's also something very relevant, important for DBpedia. It is the model that is used to capture the information that is being extracted from Wikipedia. The ontology is maintained on the mapping server. It has this kind of hierarchical form. The root class is a thing, oval thing, and then we have the other hierarchy. Here we have an example for organization with the subclass broadcaster, company, educational institution, group, government, agency, etc. Yeah, so currently the ontology contains over 700 classes and more than 3,000 properties. It is a community effort. Different people are editing and improving the ontology every day. Yeah, the mappings for the ontology are also on the mapping server, and these are just screenshots. So here is an example about the definition of the ontology class person, and also on the right side you can find the link which you can follow, and it will bring you to a page where you can browse the ontology, which is basically what I've shown you here in the previous slide. Okay, so one slide about the impact of DBpedia. So yeah, probably you have heard about DBpedia and how interesting it is, and how relevant it is if you are doing research within the semantic web community, data mining space, etc. You probably considered maybe using DBpedia. So according to Google Scholar, there are over 35,000 of articles which are mentioning, using, exploiting, or contributing to the DBpedia. I already mentioned the DBpedia and the relation to the Jeopardy challenge organized by IBM Watson, where with help of DBpedia, for the first time, a machine won the challenge against a person. DBpedia has been also part of this standardization efforts, such as the ITS 2.0 standard, Shackle, and other W3C standards. It has been also used within other standardization efforts, such as Unicode for abbreviations, translation of language codes, and other big players. They are also using DBpedia and for different purposes. So DiffBot is one of those which is using, with help of DBpedia, they are boosting their knowledge extraction process and also making use of the DBpedia identifier space. Okay, so the next part is about some practical examples about how and what you can get as an information from DBpedia. So here we have listed the three main Sparkle endpoints, which are basically services that you can use to query and get information from DBpedia KG. What is good to mention is that not all the knowledge that we have, all the information that we extract, not everything is published on this on the main Sparkle endpoint. On the main Sparkle endpoint, what you can find is the so-called latest core data set or collection, which contains the most relevant information. So all information from the English Wikipedia is published, plus some additional data sets such as links to other languages, etc. The individual information or the information from the language-specific extractions, they are not published here, but you can find them under the dedicated Sparkle endpoints for that particular language. So there is a Sparkle endpoint for the German DBpedia chapter, then there is the Italian, there is the Czech one, the Dutch one. So different chapters are maintaining their own endpoints. Then we have the Databus Sparkle endpoint. The data bus is the middleware where the data is published, not hosted, but just the metadata is being published. And there on the Databus Sparkle endpoint, you can find all these data artifacts which are regularly released. More about this will tell you my colleague Johannes in the following presentation. And the third endpoint is the DBpedia Live endpoint, which you can query in live the information that is being extracted. So this is basically relates to the DBpedia Live extraction. So as soon as some edits are introduced in some Wikipedia article, the DBpedia Live extraction is executed, and this up-to-date information is being extracted and published as part of this Sparkle endpoint. Okay, so let's look at one simple example here. Okay, so here we have a simple query. For those that are not familiar, this query is written in the Sparkle query language, which is a query language developed for querying RDF graphs. This query will retrieve several pieces of information. It will retrieve identifiers for people, their name in English, the country where they have been born, so the birthplace, and the population of the country. So the persons, their names in English, their birth country, and the country of population is queried and retrieved from the Sparkle endpoint. And let's have a look. So if I go to dbpedia.org/sparkle and I paste the query here, there are used some names, some prefixes here, DBO, for example, or RDFS for RDF schema. These are already defined within the triple store, so you don't need to define them here. And if I execute the query, I will get the list of all these people with the birthplace and the population of their birthplace. Okay. And then their name in English. So if you want, you can also filter out the names in other languages as well. That's a very simple query, but what about something more complex? What about a query that would retrieve all soccer players that are born in a country with more than 10 million inhabitants? Okay, still not so complex, let's say. But what if we want to filter out only those soccer players that played as a goalkeeper for a club that has a stadium that has more than 30,000 of seats? So if we want to query to submit such question, let's say, we can write this query. It's a bit more complex, but still relatively easy to write, I would say. And let me explain this query first. So we are retrieving the identifiers of these people that we will retrieve, their name, country of birth, the population, the team that they played for, the stadium, and the capacity of the stadium. And here are the constraints defined. So we retrieve only resources or identifiers that are type of DBO person. We retrieve their name, the birthplace, then we retrieve the population of the birthplace, which is the country. Then we look for the team that they played, and we filter out only those people that had a position or played as a goalkeeper. We also would like to filter out or to narrow down the results based on the capacity of the stadium of the team. And here we retrieve the team, the stadium, and the capacity of the stadium. We want to get only results for soccer players that have their name in English in DBpedia. We want to get also only those soccer players that played for a team that has a stadium with a capacity over 30,000 of seats. Here is this requirement also specified here in this line. And we want also to retrieve the population of the country, or get soccer players that are born in a country with population with over 10 millions of inhabitants. And we order the results according to the stadium capacity. Okay, so let's now try this query. So I'm going back to my endpoint, dbpedia.org/sparkle. I paste the query here, and here are the results. So I get links, basically identifiers for those people, their name in English. Then I get links to the country of birth, or the place of birth, basically. The population. Yeah, actually Kinshasa is the capital of Congo, if I'm not wrong. Then the population. Then we have the team here. Then we have the stadium for the given team, and the capacity of the stadium. And basically all these results are meeting the query that the requirements that we specified here in this query. Okay, so I'm end of my part of the presentation, and I will be happy to take a question or two if there are any questions in the chat. Okay, I don't see any questions in the chat, so I would suggest that we continue with the presentation and don't hesitate to write your question in the chat. We will be happy to answer any question that you might have. I will give the floor.
Yeah, hello, Milan, you just disappeared, but I think you wanted to say you want to give the floor to me. So I hope everybody can see my screen and hear my voice, which is a bit distorted by the emergency signals. So what I want to do in this chapter, I want to show you different options on how to access, download, or deploy the DBpedia Knowledge Graph. I also would like to give you an overview about services which you can deploy on your own infrastructure, like the Databus, Global ID Resolution Service, DBpedia Lookup, and DBpedia Spotlight. So the DBpedia Knowledge Graph is just a set of files containing RDF data, and there are many options how to access this. The really basic option is that you can use the linked data interface. So every DBpedia identifier is resolvable via linked data. So if you visit it via the browser, then you can you get a visual representation where you have the option also to download the data manually in different formats. But of course, it's also possible to fetch this data via the command line with a very tiny command. Okay, I just copy it from the presentation because my history is, so this is a really basic command with curl which retrieves this information from the DBpedia linked data interface, requested in triples format, and then you get all the triples which are related to this specific entity. There's also plenty of other options. So the next option has already been shown by Milan. So there are different Sparkle endpoints. He showcased the queries against the main endpoint with the English DBpedia loaded. Then there's also this live Sparkle endpoint, which behaves exactly the same but has more recent data. And then there is also a chapter infrastructure. So several of our DBpedia chapters provide their own Sparkle endpoint, which serves nationalized data. So there's, for example, a Dutch chapter, or there's also a Japanese chapter, which provides a Japanese endpoint, which also offers this Sparkle interface, where you can execute the query and then get, for example, all the data pointing to the Japanese DBpedia, respectively, Wikipedia identifiers. If you want to query the data like with Sparkle, like Milan had shown to you, I can also recommend this YASQI interface, because it has a lot of features which are quite useful. So it, for example, automatically has an index about all the different properties and classes of the DBpedia ontology. So, for example, here, if I just remove this and then I get an auto-completion where I can now see what is starting and see the, for example, now the property organization. And this also works for properties and has also a lot of built-in tools in order to visualize the data so that you can have a look whether the data is what you expect or whether it fits your quality requirements. Second option, how to get the data, is downloading the dump files via really old school file directory download. So there's a web server hosted at downloads.dbpedia.org. And yeah, there we release the new monthly modular extractions, which started in 2020 under the /repo DBpedia location, and there you can download the different extractions from the different extraction modules. Milan had already introduced, but there's also the legacy releases, which are quite important for research. So there's, for example, this 2016-10 version. I think, Milan, you're not muted. It would be great if you could mute yourself. Thank you. And yeah, but the novel approach in order how to actually solve how to resolve data sets of DBpedia is using so-called DBpedia release collections. So we have two kinds of collection. One is latest core, and one is snapshot. And a collection is basically kind of a list of files which points to identifiers on the databus, DBpedia Databus, which I will explain later, which in turn point again to files on our download server or also on other servers. And the idea here is that you can use different kind of tools which make use of these collections in order to download the files to your local server or your local infrastructure. And yeah, these collections are quite useful because they bundle basically the information which is loaded into our Sparkle endpoint. So the Sparkle endpoint does not contain all the information we are extracting, because I already said we only load the English data and also only a subset of all the files we are extracting. And this collection here represents this subset and allows you to get the latest data. But we also create snapshots every 3 months, which are basically also derived from this latest core collection, but contain data where we think it was the best release within 3 months. So I can have a quick look on how this looks like. So this is this view of this collection. You have some documentation and release notes here, and then you can see all the files which are contained in there and could download them, or you can also use the download URLs directly. But of course, using these collections, there's also a programmatic way how to retrieve this data. So a really simple strategy is this 3-line bash script. So in the first part, you just use this collection identifier, which is stated here. Just close them first. Clear. You just retrieve this collection identifier and fetch the information, which is basically just a Sparkle query of the collection. And then in the next step, you can evaluate the metadata, which is associated with this collection. And finally, you then can just use, so this parameter basically uses the metadata and passes the download location out of it. And then you can just use the last script line in order to download the files. And in this scenario, I just used an echo command. So it's not actually downloading, it's just showing the command, which would be executed. So this would be a very simple programmatic way, which can be easily transferred to every programming language. And yeah, but using these collections, you also have the option to make a fork or copy of such a collection and then modify it based on your needs. So on the right hand, you can see how I basically created a copy and then changed the language to another version, Latvian, in this example, in order to have almost the same kind of assets in the Sparkle endpoint, but for a different language chapter. Moreover, there's also the option to not use the collection, but go one level deeper to use the DBpedia Databus, which has these metadata which point to the files. And there are now two ways. One way is that you can actually use the interface, the front end, the UI, and browse the different data sets and collect the database file identifiers, like I had shown before. So there was this example collection here, and there's this files which you can use. And yeah, you can, for example, now browse all the different data sets in there, pick a version, and then again filter here for the kind of information you want, and then either use a query or use the files. But of course, you can also use the query and adopt it, or write your own Sparkle query and then issue this query against the DBpedia Databus Sparkle endpoint, which contains all the metadata which are important for the DBpedia releases. But then there's also another option that you can basically automatically set up a triple store which already contains the data preloaded you're interested in. So having in mind this latest core collection or this other snapshot collection, you just can use this simple one-line command, assuming that you have Docker and Docker Compose. And this setup will basically instantiate different containers, and one container then will use your collection, retrieve it, analogous to the way I used in the command line example, and then retrieve all the files, and then automatically insert them into a Sparkle endpoint, so that you have a Sparkle endpoint already, which is really similar to the ones we are providing on the main endpoint. Now I already have thrown many technology terms at you, like the databus and databus collections. So I want to quickly introduce them now officially. Our director, Sebastian Hellmann, really likes this idea of understanding the database as a digital factory platform, or as a global file warehouse for decentralized storage. And yeah, so the idea is that you can basically register any file on there, and the format doesn't matter, but there's this requirement that we have really strict technical metadata. It's not a lot of metadata, it's just really simple. So you have basic provenance, like who uploaded it and when, and you have to provide a license, and you also need to think about the structure, how you want to structure the data set. So you cannot just insert every random file, because we have a fixed structure, which I will explain later. And you have to think about versioning. So this is the requirements we have, but apart from that, you can upload or register basically everything. A more technical definition, if you would ask me to define the database in one sentence, I would say it's a metadata registry which was inspired by Maven concepts, ported to linked database platform. So it contains metadata descriptions and using the data ID vocabulary about all the data sets and the download locations to the actual data files. And the aim of the DBpedia Databus is to have a high, or allow a high degree of automation for publishing, but also consuming data. and especially having in mind iterative workflows that have data dependencies from the previous workflow run. The databus itself is now, since some weeks, it's open source, and it's a Docker Compose setup as well under the Apache 2 license. You can check it out via GitHub. And databus DBpedia.org is basically the DBpedia databus deployment or instance of the DBpedia Association, which basically contains all the release information and is important for us to basically maintain and run the releases and improve the quality and track the quality of the extractions. But moreover, we also capture community contributions over there. And currently, it's even possible that you register your own data there, since it's available as beta to the public. But I also would like to mention that at the moment we're using an older version for backward compatibility reasons. And if you want to try out the latest code, you should have a look at dev.databus.dbpedia.org. Another term I mentioned is the so-called databus collections. So collections realize some kind of data shopping cart, or more technical term would be a catalog of data assets from the databus. It also contains some basic descriptive metadata I had shown before, like some documentation and label and an abstract. And it makes use of this metadata of registered data assets to address a list of file IDs. So sometimes there's a confusion. So why is the databus actually called a bus? So for us, it's kind of an address bus. So it addresses the files on the web. And this allows to have very clear provenance, which makes it ideal, in our opinion, to define dependencies. So there's this collection editor UI, which can be also seen on the right, which allows you to use a kind of faceted browsing for the different data sets and their content variants, like the language, for example. And then you can apply filters based on the metadata. But moreover, you can also create copies of collections and then modify them so that they can be easily reused. And the good thing about this is that this databus collections now have this one identifier, which I was using in the bash script, which basically translates or can be resolved into the Sparkle query, which I can then evaluate against the Sparkle endpoint containing the metadata. And yeah, so there can be two kinds of collections. So we can make the collections dynamic so that they use the latest versions of data sets, but we could also use a fixed version by using the stable but redirectable database file identifiers. So the good thing about these collections, or why we actually use collection, why we propose these, is that it's a really easy way to redefine and configure data dependencies in a really transparent way. So you can easily send, okay, this is all the configuration, input data configuration for this workflow, without writing a single line of code. So the next part of my presentation is actually navigating now this DBpedia Knowledge Graph dump structure on the databus. So the databus, as I already mentioned, uses a quite strict structure, and it's hierarchically structured, similar to Maven repositories. And yeah, the top level hierarchy is basically a databus account or a databus publisher. And in our case, for the DBpedia Knowledge Graph, this is the DBpedia account. Then on the next level, you have so-called groups. Groups somehow bundle data sets which make a meaningful unit. And in our case, we have 4 groups at the moment for the modular extractions, which each represent one extraction module. So you remember there was the generic extraction, there was a mapping-based extraction, text extraction, and Wikidata extraction. Everybody has its own dedicated group. And within such a group, you can now have multiple artifacts, and artifacts just represent this abstract concept of a data set. So you have a really stable identifier for this idea of a data set. So one data set is, for example, labels, and one data set is categories. And these data sets should somehow stay stable over the time, so that you can use versioning without breaking something. So it's really inspired from this idea from Maven, where you really try to modularize your software, but then it should somehow keep stable for the next years in order to not break something. On the level below, every artifact can contain files, which represent this data set. So in a labels file, labels data sets, there should be obviously only labels files, but you can further modularize this data set by using so-called content variants. So in this case, we, for example, use the language as one content variant. So we split the labels based on the language. And we also do the same basically in almost every artifact. So the language in this case states the Wikipedia version which was used. So Russian is obviously then the Russian Wikipedia version, and English is the English Wikipedia version. Moreover, there can be also formats and compression variants. With regard to the DBpedia, we almost always use a simplified turtle serialization format and BC2 compression. So having this structure in mind, I would like now present some prominent DBpedia knowledge graph artifacts which could be useful for your own projects or for your own science or whatever. So first of all is the labels artifact, which contains more than 130 language versions, and as I said, it's using this language content variant, you're easily able to select the kind of languages you're interested in. So you can also, for example, select Japanese, Arabic, and English, for example, and then basically only retrieve the files you're interested in. This is particularly useful, for example, for visualization purposes or creation of semantic dictionaries or indexing for search. Another popular or useful data set is the so-called geocoordinates data set from the generic extraction, which allows you to create map visualizations. In this example, I, for example, plotted all the stadiums which were contained in DBpedia and having a location. And it was quite interesting to see how they basically are spread over the world. And you can also use it to make area-based or neighborhood-based retrieval of entities. So the Virtuoso Sparkle endpoint allows geo-indexing, which you can basically define a rectangle where you want to query all the entities which lie in there. The most, or one of the core parts, is also the instance types, because usually you're having a kind of domain focus and you're interested in some specific kind of entities. This can be done with the instance types, also called A-box, and they basically represent the mapping between the DBpedia ontology. So on the bottom, you can see a visualization browsing through the ontologies, and on the right, showing how many instances they have. For this extraction, we, for example, use additional content variants. So they're specific, which means only the most specific type is included in this file. And then there's transitive, which also contains all the upper classes. So every politician will be a person. So there will be also this person statements materialized in this file, which makes it easier to query. Then there's this mapping-based objects and literals, which have two different data sets. With regard to objects, there's also two different content variants additional here. One is disjoint domain and disjoint range. In case the definition does not apply. So for example, if you have a daughter and the daughter is actually not a person, then we will put this in this disjoint range, letting you know that this fact might be not accurate, but you can still decide whether you want to include it or not, depending on whether you've selected or not. And then there's also literals, which contains all the facts which are of string or numeric nature. And one I would like to mention here, that numeric measurements are normalized to the base SI unit, so you can easily compare them across language versions. So we're not using feet, we're using meters all the time, which makes it easy to query facts and entity relations across all the different language versions of DBpedia. And yeah, if you want to retrieve the DBpedia ontology, there's also an artifact for this. This link here points to the developed version. So you saw this mappings wiki where you can edit the ontology. And whenever you edit something, then there will be a new development version release. And this is powered by DBpedia Archivo, which is a dedicated ontology archiving agent on the DBpedia Databus. And it persists and it crawls, monitors and persists ontologies and archives them and versions them in a unified way. And you can have access via the ontologies agent, and then every group represents the domain of the ontology. So in this case, it's dbpedia.org, and then you have the path forms the artifact version, and there's a suffix def for the ontology, and the version in our case is the timestamp. So here you can see that although the structure is somehow fixed, you can try to have a meaningful separation of your data and structure it in a way so that it's easily reusable. There's also an API for this to make this more easier, which is provided by Archivo, which allows you to retrieve the latest version with a single URI. Another really important artifact is the so-called same as links artifact. So we have two kind of data sets here. We have same as all wikis and same as external. Same as all wikis contains all the linkings or entity relationships between Wikidata and DBpedia. And the external contains all the links between Wikidata and external links. And you can use this information to write federated queries, to do knowledge fusion, or you could also use it as a popularity indicator. So the more links you have, for example, usually the more prominent the entity is in the different Wikipedia versions, which is kind of an indicator that's an important entity. But when it comes to these links, we also offer another service, which is also loaded in the main endpoint, which is called DBpedia Global IDs. So based on the aforementioned links, we compute connected components and basically form clusters of equivalent entities. And then we assign every cluster an identifier based on the lowest cluster member identifier. And we have a microservice in place which allows you to type in different identifiers like for example, the different Wikipedia identifiers, and it then will show you all the different members in these identifiers. All the identifiers in this cluster, sorry. But there's also other options in order to retrieve identity information. So on the one hand, there is DBpedia Spotlight, which will be showcased later. So it allows you to translate text and perform entity annotation. Where's English? Which are then automatically linked to DBpedia identifiers, which you can use to then retrieve information about it. And there's also a DBpedia lookup, which is a kind of free text index and allows to perform a keyword search for entity retrieval on the DBpedia data. So there's different API calls. One is for prefix search and the other one is for autocomplete. This will be probably also shown later in the use case. So, but the second part of this chapter is that you can basically almost every of the aforementioned service are now easily deployable on your local infrastructure using Docker Compose. Since we're using unified technology stack, which is founded or based on this databus and databus collections. So we have an on-demand Sparkle store, we have an on-demand lookup search, we have self-hosting DBpedia Spotlight, and we have a download client which has CSV to RDF conversion. All the containers usually use a similar strategy or architecture. So you have an application container, which basically waits for data or wants to consume data. And then there's a download container, which downloads this data based on, for example, the collection identifier or Sparkle queries. And then there can be other helper containers like a database, which is then where the data is propagated to or loaded to. So one example is this quick start, which also Sparkle endpoint quick start, which allows you to load any collection to a Sparkle store, and which we also use and ship to our DBpedia chapters in order to load the versions, the local language versions of their DBpedia data, and make this unified and make sure that everybody uses similar versions. There's still a migration, so not every chapter is using this so far, but I think we are quite happy that we made huge progress here. And the interesting thing is that this service one-liner basically allows you to define the collection URI and also the databus Sparkle endpoint. So you can set up your own databus and then use this with your own databus, or you can use the official databus and the official collections. So it's easy, adoptable for your use case. Then there's this on-demand lookup, which we show later, which allows you to perform entity search. And it's composed of a download container and a lookup container. And the data is basically loaded into a graph database to allow a Sparkle access. And then you can define Sparkle queries in order to fetch information and index them in a Lucene database. And this is all configurable via YAML files. And we even have a really simple default config, which indexes all the labels, which basically works more or less out of the box. The aforementioned services were quite generic, so you could use it with any RDF data, but also, of course, with the DBpedia data. DBpedia Spotlight at the moment is only dedicated to DBpedia data, and it allows you to basically download language models of Spotlight and then use it on your local infrastructure to have full control over it and to not have any quota or API limitations in place. And finally, there is this database client I mentioned, which is an enhanced consumer-oriented download client for this database. Our vision here we are following with this is the idea of a local compile and install. So you basically define a collection, and then you define your target format, your target compression, and then it will automatically fetch all the data sets, try to decompress it, to convert the serialization format, optionally map it. For example, if you have TSV files included in your collection, it will try to convert it to Turtle and look for mappings registered on the database. If there's no mapping existing, it will just apply a generic mapping and transform it to an RDF format, in this case Turtle, and then go down again, apply your desired compression format and write everything out so that you can consume it with your service or workflow. Yeah, thank you very much. This is the end of this chapter. I'm happy to take questions. Are there any questions so far? Okay, Michael, the questions about the visualization, ontology, transitive, and inherit, how does that look again? I just go back to the slide, but maybe you could specify a bit more. So the visualization, the idea why we use this two different kinds of data sets is that usually SPARQL endpoints allow some kind of reasoning, but it makes the query execution slower. So the idea here is that we separate the data in the most specific type, and the transitive type is only to find all the data, to find all the all the entities which belong to this class. And this visualization here makes use of this. So in the official SPARQL endpoint, we don't have this reasoning enabled, but we load the most specific types and we load the transitive types.
I'm not sure. Can anyone see on the screen? I cannot.
You cannot see it anymore. Okay. Oh, it was interactive. Yeah. So this was interactive. Yeah. It's not running right now, but because it was a Google Summer of Code project, I think Jan, you mentored this. Maybe you know more about this, but as far as I know, it's using this SPARQL endpoint. So in this case, it was DBpedia endpoint, and then generates some statistics. But I think the stats were materialized, right? So it used the SPARQL endpoint to materialize the stats. So it's not using on-the-fly SPARQL queries.
Yeah, if I recall correctly, this was pre-baked. Yeah.
But it would be possible, of course, to recalculate it, let's say every night, for example. All right, thank you. Are there any more questions? Milan, what do you think? Shall we make a short break now? I think it would fit quite good before Jan starts, so that everybody can get a coffee or water or whatever.
Yeah, well, we think. Well, I think we can continue, or maybe just take more questions if there are any. We are under time pressure, and we have still the part on the use case. So my suggestion would be, if there are no questions, to just continue.
Okay.
Okay, good. So the next presenter is Jan. with his presentation on the use case using DBpedia.
All right. So I'm going to share my screen. So this is working, I hope. So yeah, hi everyone, I'm Jan Vorberg, and I will take you to the chapter 4, use case, semantic indexing and search using the DBpedia technology stack. So I have the noble task to make a small live demo, fingers crossed that everything works well. Our goal here is to use the DBpedia technology stack that has been presented to you earlier. Not everything, but at least some of the parts. And that includes the DBpedia Databus platform, the DBpedia Spotlight for entity and text annotation, and the Virtuoso Quick Starter module, which is the on-demand triple store. We are going to use some example resources in this tutorial, which with some basically dummy text inside. This example can, of course, be applied to more useful things, just as a note. The general idea, what we want to do here in this tutorial, we want to filter documents based on their content. And inside of these documents, we have some plain text. And now we want to sit and think, can we do more than just searching for the words in this document? And this is not a new task, and this is nothing significantly new. But of course, you can do entity classification and tagging. So you find some words in this text that have some meaning, assign some identifiers to these words, and then link these identifiers to some other complementary data to make more sophisticated queries on that text. So let's try to do this with the DBpedia technology stack and the technologies that I listed before. Let's try to apply some geospatial queries to topics in the text documents. So as the complementary data, we take some geospatial data. Then we do entity classification, entity tagging in our documents, link that all together, and then we try to make queries based on a certain area on our documents. So queries like, give me all the documents that talk about a topic that is specific to a certain area. The tools that we're going to use is a command line interface, a Google or GitHub account to log into the databus. Then you would, in order to follow along, would need Docker and Docker Compose installed on your system. A web browser is helpful. And let's skip the optional part. We can do this without that, without a GitHub account with GitHub.io. All the data that we are using is already hosted in a GitHub repository, and we can use the data from there. If you're unable to follow along, there's certain steps that you can still do. Also, we have the same databus that we're now going to deploy locally on our machines, or on my machine, is available on dev.databus.dbpedia.org. The link will be in the slides, where you can take a look at the databus and also log in with your GitHub or Google account. There's a resources repository available that is sitting in this URL. If you have the slides, just click on it. It's at dbpedia/tutorials master CDW21. There you can find all the files that we are going to use in this tutorial. So first step would be to run git clone on the repository and navigate to the CDW21 folder. I have already prepared this, so here we can see what's in the repository. We have two folders, one called databus and one called store. Those are the Dockerized applications. The only content they have is a Docker Compose file, which is sort of the startup configuration for our containers. Then we have a texts folder with our documents inside. Everything that ends in txt will be the documents that we are trying to annotate. And then the Spotlight annotations nquads file is basically an intermediate result that we are going to use later. Then we have the annotate bash script, and the annotate bash script we will take a look at in just a few minutes. So let's go back to our task. We want to filter plain text documents based on a specific Sparky query, and in this specific case on a geospatial query. Here are the steps. that we are going to go through. So first of all, we're going to start a local databus on our machine. Then we publish some geodata on that databus. Then we find some documents. Well, we already found them. They are in the example repository. We're trying to annotate these text documents with DBpedia identifiers using DBpedia Spotlight. You can run your own DBpedia Spotlight on-premise or on your local machine, but in this case, we are going to use the service that is hosted by us. Then we upload the annotations. Also, this we can skip because we already have this in the GitHub repository. Then we publish these annotations on our databus. So we tell our databus where these annotations are located. And then when we have both the geodata and the annotations on our databus, we can use a databus collections to aggregate this, take this collection identifier, load it into a triple store altogether, and then we can send Sparkle queries against that triple store that is running also on our local machine. So let's get started. First of all, let's choose the complementary data. I wanted to quickly mention this. We already went through these different extraction modules and that there are different artifacts containing geospatial data or the geocoordinates. And there's the mappings group that contains it, and there's also the generic group that contains it. And these geocoordinates artifacts, they differ in, well, the extraction method that has been applied. In the mappings group, you will find the geocoordinates that are used with a mappings extraction, and they are more precise because they're using mappings from the info boxes. Generic, well, you have more data, roughly about double the data, but less precise. We are going to use the latest version of these geocoordinates, downloaded from the DBpedia Databus. They are also contained into this example resources repository. And since mappings is more precise and also smaller, it was better suited for this tutorial to speed everything up. This is what it looks like if you visit dbpedia/mapping/geocoordinates mapping based on the databus. Johannes already showed this with the file browser, and there we selected the latest version. So first step, let's start a local databus and publish the complementary data, and that is the geocoordinates dataset. So let's hop into the command line. Let's navigate to the databus folder, and in here we have just a Docker Compose YAML file. So for everyone who does not know what that is, oh, this is still not quite correct, I think. Well, apparently it is. Sorry about that. We have this Docker Compose file that specifies all the containers that we are going to start. So Docker Compose file is a configuration file that lets us start multiple Docker containers at the same time, and then also specify how these containers interact with each other. For the databus, we need one container for the main databus application, and then these other two containers are database. The GStore is an intermediate database layer where data is sent to, and then the GStore persists that data into a Git repository and also into a triple store. And that very triple store is this Virtuoso container using an image from 10for's Virtuoso. Right, so before starting, let's take a look at the configuration file first. So this Docker Compose configuration file has another meta configuration, which are the environment variables. And as these are environment variables, it's important to set a couple of parameters. So we want to use our databus resource base identifier. So all the identifiers generated for our database start with that prefix. And that will be HTTP localhost 3000 because we are going to host this database on our localhost. And then these configuration parameters, which are specific to OIDC login. On the databus, you can log in using OIDC. If you don't know what that is, send that to your DevOps people, and they can give you the OIDC, or most likely give you the OIDC credentials for whatever service you're using for authentication. So let's, in this case, we are using an Auth0 OIDC provider that supports login via GitHub account or Google account. So let's pray to the live demo god and start this. You can see the databus is waiting for the database to come up. We can see the GStore and the virtuoso initializing. And now that everything is up and running, the database starting. And let's try this again. And apparently this time, no, all right. So apparently I had still some Docker containers running in the back. So I'm just gonna delete the data folder, run our Docker compose stop, and the Docker compose remove. Make sure that nothing is running. Wonderful. And let's try this again. If that fails us, we are just going to the dev server and using the databus there. There we go. So databus started, is starting several threads, and now our databus is running on localhost 3000. There we go. There's a clean databus running without any data published on it so far. And we are going to change that. First of all, I have to claim my namespace. So the first path segment in every resource identifier that I'm going to create will be my username, and that I have to specify first. So I'm going to go with Jan here. And here I have my account. So my account identifier is now localhost 3000/Jan. So let's add this complementary geodata. And here I'm going to create a new databus group. I'm going to call this the CDW tutorial. Let's be a bit sloppy with the documentation here. Let's create a new artifact. I'm going to call this geocoordinates. This is going to be the DBpedia mapping-based geocoordinates. And let's again skip the documentation step. I'll assign a version based on today's date, assign a license, add some more documentation. And what I'm left now with to do is to add the file. And so I'm going to the CDW GitHub, the resources GitHub repository that I posted earlier. I select this file that I uploaded to this repository and add this URL and tell the database where that file is located. Here I'll now have my file in the TTL format, and BC is to compression that has been auto-detected. What's left to do is to analyze a file URL without any apparently, since I'm streaming now over to my screen to the conference, this takes up a bit of the power of this machine. So this takes a bit longer than initially expected, but it seems to be working. And now that this is ready, we can take a look at our metadata that is going to be published in the JSON LD format. And since we are happy with this, I'm going to hit the publish button to publish this to the databus. Let's hop to the front page. And here we can see our new artifact on the databus. All right, let's continue. Let's find us some text documents. Well, we already have this. They are located in the texts folder in our repository. Let's continue with step 2 right away. Let's annotate the text. And Johannes has already shown this interface here where you can annotate plain text with DBpedia resources. And let's take some of this text out here and go to the API, check for annotate, try it out, and I enter the text here because we want to have a look at what the return result of this API looks like. So we want to annotate this text that I just copied from the example. I want this returned as turtle, for example. And if I hit execute, I can take a look here what this returned RDF looks like. And here we can see several entries of annotations that specify a certain character offset in the text that we provided. So for example, from character index 0 to 6, we have the string Berlin, and this has been assigned the resource identifier dbpedia.org/resource Berlin. All right, let's take a look at the bash script that I provided in the resources folder, and let's see what it does. In here, I have the resource URIs or the document URLs of my text documents as a list. I iterate that list over here and send a request to the DBpedia Spotlight API that then will give me back the result as n triples. So this will be a triple of annotation, this property that specifies the annotation, and the topic. So for example, this triple here, right? So it will give me something like dbpediaspotlight.com offset 06, and then this itsrdf ta ident ref to dbpedia.org resource Berlin. And then since this identifier is generated on the fly because I detected something from character 0 to 6, this might as well occur in some other document, right? So the other first 6 characters might describe something else in another document. I want to make this specific to my document, and therefore in my annotation script I create quads and assign also a graph and group all these triples together in a common graph. And as the graph identifier, I take the document URL, right? So I'm doing some bash magic here and inserting my document identifier at the end of each triple that I have returned. So let's go ahead and run this annotate script. And the result that we get is in here in the texts. Oh, okay, this is a bit hard to see what's going on. Let's take a look at the first line. We have our offset 0 to 9, for example, and then something with Melbourne. And this is contained. Let's take a look at the graph identifier. The last entry in each line is the document identifier of the Melbourne text file. All right. Next step, upload the annotations. Well, we have already done this. This is already in the GitHub repository. So I did some preparation work. Let's continue with step 4. And also you can take this file from there. Now let's publish the annotations on the databus. So let's make another publish on our local databus, excuse me. Publish data. There's a button to reset the form to prevent any caching from interfering. Here we have the option to use an already created group and an already created artifact, and in order to just add a new version. We want to publish it in the same group, but we want to create a new artifact. So let's call this annotations. Gives that some name. Let's be sloppy again with the documentation. All right. Now, a cool thing that we can do, instead of entering all the files here one after another, we can go to some Git folder with a list of documents in here, post that into the first input field and hit fetch URLs. And here we can see all the files in that folder. So we have our text documents and we have our Spotlight annotations enquotes file that we generated. First, let's hit analyze on each of these files. And now we still have a problem. And that means that here indicates that the databus cannot successfully distinguish all the files that we have added here, because the databus does not look at file names to distinguish files. It only looks at certain so-called content variants. So one content variant would be a format. This is why this is valid, because it has a different format than the rest. It can also distinguish by the compression type. And if we still want to distinguish files that share the same format and share the same compression, we will have to add content variants ourselves. Previously, you have seen, for example, in the labels artifact, that these are distinguished by languages. So there has been a new content variant added that is called language. And then as each content variant, we added these language shortcuts like EN for English, JA for Japanese, and so on. So we will have to do the same thing here. I will add a content variant called topic, for example. So this is obviously about Berlin. This is about Melbourne. This is about San Francisco. And this does not have a topic. And I also want to add another content variant that is called annotation, and that will indicate if that document in this artifact is an annotation. So this is no annotation, this is no annotation. And this last one here is an annotation. Let's take a look at the metadata that is being sent to the API. And here at the bottom, we can see these extra content variant properties. So one for topic and one for annotation. Also here in the list of the files that we are going to add in the distributions list, we can see that they use these new properties. Let's go ahead and click publish and head back to the main page. And here we can see our annotations artifact and the faceted browser. Here we can see the default facets like the version, the compression, and the format, but now also our custom content variants. So for example, the topic, where I can filter only for the topic San Francisco, or give me only the files that are really part of the annotation. Okay, cool. Now, next step is to aggregate our geodata set and our annotations. And we do that by creating a databus collection. Back to the databus. And up here, we can go for collections. I delete this collection that I created earlier. That was still in my browser cache. And I go for a new unnamed collection. Up here, we can enter some data, for example, and the identifier. This will also demonstrate where your collection will be visible. So CDW tutorial, and my collection will then be at, oh, this is actually wrong. This will be at localhost 3000 Jan collection CDW tutorial. Bad case of URL hard coding here. Some abstract and description. You can also add markdown here to make a better. Let's add a list to add a better documentation. And in order to let the collection actually do something, we add a group and artifacts. So here we can search for CDW and we can find our artifacts, the annotations artifact we want, and also the geocoordinates artifact. Let's head back to editing. And here we can now see a tree view of our collection. This is the group CDW tutorial, the artifact annotations, and the artifact geocoordinates. So this selection contains all the 4 files that we published, right? So they're all the text documents that we annotated and then the annotation itself. And here we only want the annotation. We can expand the node here. Here's a input field for adding some restrictions. So for example, annotation, and we only want the annotations. So in this dropdown, we can see all the content variants, including our custom ones. So let's collapse this, and here we go. We have a collection only containing our Spotlight annotations and our geocoordinates. Let's commit this collection to save it to the database and also unhide it, so it's also visible on my profile page. Here we can take a look at a couple of things. So for example, the preview will render me a preview of what the public view of my collection looks like. I can take a look at the query that this collection translates to. So if I send this query here to the Sparkle endpoint, if I go to Sparkle endpoint here, I get the exact same results, these file identifiers, the file download URLs. Also note that these identifiers are not GitHub identifiers where the files are actually located, but these are artificial databus file identifiers. These file identifiers will then be redirected to the actual download URL. And these file identifiers also show that there's Spotlight annotations, topic non-annotation, yes. So this gives also, the file name gives some additional information about the content variants. Let's go to our collection and click this link. And you've seen this view before when we showed you the snapshot collection and the latest core collection. This is the same thing, but with our own collection with some rendered markdown, the data table, instructions to easily download this using Bash script, and so on. All right. We created a databus collection containing your data. Now it's time to load that collection to a local triple store. And for that, we are navigating to the store folder. Here in the store folder, I have another Docker Compose file that I'm going to take a look at here. Again, in this Docker Compose, we configure 3 different containers. One is responsible for downloading our collection. One is just a database, so a Virtuoso triple store. And there's a loader script that picks up the downloaded data and puts it into the store. There's some configuration we can do. The most important configuration, let's ignore all this top section, and the bottom section is what we want to take a look at is this here, the data settings. And here is our most important environment variable, which is the collection identifier. So if you follow this tutorial, you might have to change this to be to match your collection identifier. I chose the localhost 3000 Yan collections CDW tutorial. This is where my example collection is sitting. Also, I have to specify the Sparkle endpoint, and that is also running locally on my localhost 3000 /system/Sparkle. All right. So let's go ahead and run Docker Compose up to start this whole configuration. Here you can see the download container, sending the query, downloading the files that are specified, which is the geocoordinates mapping based and the Spotlight annotations. Store is starting up. And now the loader is going to work and is putting the files that have been downloaded into the store. And I think already I should be able to visit localhost 8890/Sparkle. This is where the default Spark endpoint of the Virtuoso container sits at. And this is already up and running. I will give it some more time to load data into the store so that our queries actually work. But let's go ahead to, I think, the last step that we are taking, and that is sending some queries to verify that everything worked as expected. So first of all, let's take a look at what we actually referenced in our annotations, or what we actually did with our annotations. This query selects the document and the annotation, the annotated object, and we are looking for all the quads where the graph is the document, the graph identifier, and where the actual triple is something annotated with this property to some object. So if we go back here to the API example, right? If you recall this, try it out, Berlin, try with n triples. Okay, doesn't want to do what I want. Here. So in Turtle it works. We have this triple offset 06 TA ident ref to Berlin, and this is exactly what we are looking at here in this query. This TA ident ref. All right, let's send the query. And here we can see the documents. So for example, the Berlin TXT, and there's all the resource identifiers that have been found. So text Berlin somehow it contains a mention of Spandau, and therefore the Spotlight tagged this with dbpedia.org/resource Spandau. Also, for example, the San Francisco is annotated with California. Now that we also have this geo-coordinates data set in there, we can now also request document identifiers based on geospatial queries. So let's take this one here. So here we can see we select a document. We select the same information that we selected with the previous query, so a document identifier and a resource. And then we also want that this resource has a latitude of this variable, and this variable that will then be filtered to be less than 0. So we are searching for everything that is on the southern hemisphere, if I'm correct. Yeah, hope so. So let's run this. And as expected, we are not getting the Berlin text, we are not getting the San Francisco text, we are only getting the Melbourne text back. And let's try another query here to also check this for the longitude. I think there's also more sophisticated queries for areas and distances that you can do, but let's stick with really basic examples here. So here I only want the documents that mention something that has a longitude of bigger than 0, less than 20. And also, as expected, that only matches for Berlin, or not only Berlin, but also all the other resources that have been associated with the Berlin text document, like Spandau, Germany, the Berlin identifier itself, and so on. Whoops. Didn't mean to do that. Never mind. Some future work I just wanted to point out that it's being worked on is federated collections. We had now the problem starting our own database, databus, that we also had to take an artifact already published on the DBpedia databus, download that file, and then publish that file on our databus again. And that is a sort of a process that is not really so useful and really difficult to do for all data that you might need. So in order to simplify this, we are planning to introduce federated collections that can not only make a query on a single SPARQL endpoint, so only our own databus, for example, but on multiple databuses. And this query will then be sent to our databus and also the DBpedia databus, and that makes it a lot easier to aggregate these different data sets and put them into your local Virtuoso for querying. That's it from my side. So if there's any questions in chat, I would be happy to answer them. Yeah, sorry, I had to rush through all this a bit because we were a bit short on time. Yeah, the resources are available with some description in the GitHub repository and also in the slides. So if you want to follow along at a later stage, feel free to do that.
Okay, thanks, Jan. I see no questions in the chat. Yeah, if you want to follow up on this tutorial, feel free to join our Slack. There are links in the chat, and also there is a link to the DBpedia forum. So we would be happy to answer your questions there. Yeah, let's continue with the last part of the presentation of the tutorial and wrap up the tutorial. Let me share my screen. Okay, good. I think you can see my screen, right?
Yes.
Okay, perfect. So let's wrap up. So what topics did we cover in this tutorial? So we started with something very generic, very general about DBpedia. You have learned that it's a community behind DBpedia. It's a community project, crowdsourced community project. A lot of people working on a single technology, which is DBpedia. DBpedia is a knowledge graph, but also a technology. It consists of a platform, processes and services that have been developed over the past almost 15 years. It's a wide community behind, multinational community spanning over the globe. There are people from all around the world contributing to DBpedia and using DBpedia. So it's kind of a network of people and organizations. You have learned also that about the process of how DBpedia is generated and released, so that there is this extraction framework and regular releases which are published on the DBpedia Databus platform. And also you have learned about how the DBpedia KG is organized into different data sets, partitions, artifacts, and these artifacts you can find on the Databus platform. Everything is open source and free for use. You can use the knowledge graph as well as you can use the technology, which is the services and also the platform, which has been recently made open source. Jan has also represented very nice use case on how you can use these different technologies around DBpedia to implement a use case on a semantic indexing and search, which is also very interesting and very relevant. Some few useful pointers before we finish with the tutorial. The main website of the DBpedia is dbpedia.org. Feel free to visit this website and find all relevant information. You can also join our DBpedia Slack workspace. There are different channels dedicated for different parts. You can also join our DBpedia forum. There is also a DBpedia Development Bible, which is available at dev.dbpedia.org, where you can find more technical documentation. And if you want to follow up and being up to date with the latest advancements around DBpedia, you're welcome to subscribe to our fabulous DBpedia newsletter on the link in the slide. Yeah, so how to join? You can either join and establish a DBpedia chapter on a particular language, particular domain or region. You can also become a DBpedia Association member. There is a link in the slide where you can learn more about the membership and how to join, or just drop us an email at dbpedia@infi.org, and we will be happy to send you some materials about this. And last but not least, you are welcome to contact us if you need any professional services such as training, consulting, or self-hosting DBpedia. We would be happy to help and assist. So with this slide, I would like to thank everyone for joining. If there are any last-minute questions, let me check in the chat. I don't see any. So yeah, let's wrap up. Let's conclude the tutorial here. Thanks all for joining, for following us in the past 2 hours. It was great to be part of this great event, and thanks for the organizer for having us aboard. Thank you all, and have a nice day.